Okay, great. Okay, well, yeah, hello everyone. Welcome to this reading group today where we'll be going through Llama 2. Obviously, if you're up to date with the LLM space, then probably you've heard about this. I think every single person in AI has probably tweeted about this in the last week or so. Yeah, so I thought just today we'd go through, I actually was going through this paper in the last few weeks. Well, no, this week I should say. Mostly read it on a flight and haven't got my head around every single aspect of it. It's about 80 pages long. So I thought today we can go through the first kind of 30 or 40% or so and just kind of get familiar with all of that. And then we can aim to continue this next week where we then, where we then go through the rest of it basically. So yeah, also just to check, sorry, so everything's all good on the live front, James, just to double check that before starting. Yeah, okay, cool, awesome, cool. Okay, yeah, so without further ado, today I'll be going through, Llama 2, which is this open foundation and fine-tuned chat models recently from Meta. So diving into their abstract quickly, so what they say is that they develop and release Llama 2, which is a collection of pre-trained and fine-tuned large language models ranging in scale from 7 billion to 70 billion parameters. They call their fine-tuned, one of their fine-tuned LLMs, they call Llama 2 Chat, which is specifically for this like ChatGPT style interaction, which are then optimized for dialogue use cases. They say that they outperform open source chat models on most benchmarks they tested, although we'll see that some of these are somewhat subjective. And then based on their human evaluations for helpfulness and safety, may be suitable as a substitute for closed source models. And then they provide a description of the fine-tuning approach and some safety improvements and so on that really then add on to this whole process of taking the initially pre-trained model and really running it through lots of extensive testing and validations and RL, etc., to make sure that it's safe and human aligned and so on, which is really where most of the work actually comes from. Kind of when you look at the content of the paper, the pre-training phase, which gets most of the heavy lifting done, is relatively simple and off the shelf. And then where the magic comes in is more about the product side of things, like making it consumable and safe and helpful and stuff. But yeah, we'll get into that more soon. So basically, it's an updated version of Llama 1. It's trained on a new mix of publicly available data. Basically, I mean, as we'll see, the architectural changes aren't that different. The main things are that the data itself has been cleaned and increased. They doubled the context length and a few things like this. So nothing too conceptually new, but I suppose kind of just slight tweaks here and there that have really pulled the performance out and improved it quite a lot. And then they have this chat version as well, optimized specifically for dialogue use cases, inspired by ChatGPT, etc. So the first thing they do on their website and on their paper as well is kind of throw some quick results at you without really giving the context. In fact, most of the figures say, here's the results, look in the appendix to learn more about them, which I have not gone into yet, so we'll kind of look at them from afar at the beginning. Again, so this is what's on the website. So Llama 2 trained on 40% more data than Llama 1. That's kind of the big headline there, with double the context length. So during pre-training, it's 2 trillion tokens, so big pre-training phase. Context length, which is double, so it's now 4,096. And then they do this supervised fine-tuning, which we'll explore a bit, and this human, which is over 100,000 supervised fine-tuning examples, which is training it to behave in this kind of chat-like way. And then they have over 1 million human preferences, which are these binary decisions that they then use for the reinforcement learning with human feedback, which again, we'll touch on, but we'll kind of get up to the PPO style and then probably stop for today, because there's, again, quite a lot to unpack. Anyway, so that's this kind of, 50,000 foot view of the results. They also present a ton of results. Again, this is all on the website. So the benchmarks, Llama 2 outperforms other open source language models on many external benchmarks, including reasoning, coding, proficiency, and knowledge tests. So in this case, again, this is taken from the website. They haven't directly linked to all of these, but of course, if you Google what each of these is for, then you'll be able to see which of them are related to reasoning, coding, proficiency, etc. But the kind of immediate impression is that, I mean, it says in the top left, higher is better. So Llama models are these ones in blue. In fact, Llama 2, so I mean, you can see obviously Llama 1 is actually the second from the right, but all of the other blue ones are Llama 2. and higher is better. So when you look across each of the rows, you see that generally the Llama results are the highest values, and they are therefore performing better than the other open source alternatives that are out there, such as MPT and Falcon. Well, in this case, only those two are compared to actually. They've omitted GPT-4, etc., but they say throughout the paper that GPT-4 is better on almost all of these metrics. So I think that they're quite competitive with GPT 3.5, but not on GPT-4's level yet. Yeah. So this is kind of, again, 50,000 foot view of some of their results on various benchmarks covering a whole load of different tasks. So then when you dive into the paper, the first few figures that we see are, again, a few kind of high-level quick results on how well it does, before then getting into the details and the meat of actually what's going on. So for this one, it's an internal test they do where they look at the helpfulness based on a human evaluation. And basically what they do is they ask people to kind of score, you know, is this one more helpful? Is this one more helpful? Is it a tie, etc.? So you can either say, you know, A is more helpful than B is more helpful than A, or they're equally helpful. And this is based on kind of Meta's you know, just guidance on what is helpful, basically. So that they do acknowledge here that it's important to take note that human evaluations can be noisy due to limitations of the prompt set, subjectivity of the review guidelines, subjectivity of individual raters, etc., and, you know, the inherent difficulty. But nonetheless, regardless of how seriously you take the review guidelines and how objective you can treat it, their point being here that compared to ChatGPT 0301 and Palm and Falcon and Vicuna, etc., and MPT, that they are providing more helpful responses on average compared to all of these. This is their takeaway. But again, like, it can't be completely decoupled from the subjectivity and the, you know, the bias that might be injected, given that it's Meta that have, you know, that they've written the guidelines basically on what is helpful. Something a little bit more objective then, and again, the details of all of these come in the appendix and everything. So obviously, you can unpack the exact specifics for all of these. The takeaway here is that this is now more objective, because actually the helpfulness is decided by GPT-4, and it's decided by GPT-4 in a way where the model responses are randomly swapped, also to alleviate bias between which one or anything like this, in case, like, you know, GPT-4 generally thinks that the first response is normally more helpful than the second one or whatever. I don't fully understand why. I guess the win rate is the win rate of the competitor, because they make this point that Llama 2 is better in the green region, which is a low win rate percentage. So it's a weird way of framing it, but I guess it's so that they can kind of bring everything close to the origin being good. But that would suggest then that the win rate is for the competing models, and therefore what we get, for example, in the very lower left, is that Falcon wins almost never against Llama 2, and this is based on helpfulness and safety, and the judge of whether it's helpful or safe is GPT-4. Basically, like, is this more helpful or is this one more helpful, etc., with randomized order. So this is actually a pretty objective metric, because there's no way that, you know, the review guidelines that Meta have put out or anything can start distorting the data here. So again, it suggests that I think this is something to be trusted more than the previous one, personally, or it's certainly a better, more objective measure of kind of helpfulness, basically. Yeah. So yeah, any quick questions? Well, quick or long questions so far, just on this 50-foot view of the results? No, cool. Okay, I'll keep going. Another 50-foot view of the results. So basically, again, what was this? I'm trying to remember now. So it's again safety human evaluation. So this, yeah, just about safety, not about usefulness right now. Compared to other open source and closed source models, human raters judge model generations for safety across 2,000 adversarial prompts, both single prompt and multi-turn prompts. Yeah, so again, somewhat subjective here, because it's human raters judging it, and again, these are human raters that are operating on the guidance that Meta has given for the scoring. Obviously, in good faith and presumably not especially biased, but there's more avenues for bias creeping in, obviously, if it's the same guidance that was used for part of the reward modeling, that's training model, for example, which is also the case. But yeah, it's important to caveat that these safety results with the inherent bias of LLM evaluations due to limitations of the prompt set, again, subjectivity of the review guidelines, etc. So again, I wouldn't take this one as quite seriously, but again, what they're basically showing is that in terms of safety, the Llama models make fewer violations based on the safety guidelines and metrics that the reviewers were using by Meta. But again, I think the point here is that that might align with the reward function that was literally used to train Llama. So if the guidelines are subjective, like you might end up having it, petering towards what actually was used to train this model, and of course, therefore, it would perform better in the end. But still suggesting that this is a particularly useful and safe model compared to some of the open source variants, nonetheless. Okay, so I went into the architecture a bit as well. What I actually realized, it doesn't make sense to talk about the architecture without quickly looking at Llama 1, because basically it's the same with a few small changes. So I dived into that a few hours ago and had a bit of a look at the main points here. So the first thing is not much has changed, again, as we all know, in terms of network architecture spaces since 2017 when it comes to transformers. Basically, they say, following recent work on large language models, our network is based on the transformer architecture. We leverage various improvements that were subsequently proposed and used in different models, such as Palm. Here are the main differences with the original architecture and where we found the inspiration for the change, in brackets, basically. So there's three main differences to the canonical one from 6 years ago. The first one, which has been common for a long time, is pre-normalization. So to improve the stability, they instead normalize the input of each transformer sublayer instead of normalizing the output. And they also use this RMS normalization function, which again was introduced quite a while ago and has been using transformers for a while. I mean, high level, let's look at this. High level, you have your transformer architecture like this. That the original one had this add and norm that came after the attention layers. Basically, now the normalization comes before. Correct me if I'm wrong. I actually put it on the feed forward as well. I don't know if anyone knows this and can correct me, because I'm not sure if it also applies a normalization pre-feed forward or if it's only before the attention is the default approach right now. Does anybody know that? Okay, well, maybe check out the paper, but certainly on the attention, it's like anyone reading, I mean, feel free to check out the paper to get the answer to that. But yeah, basically the main takeaway is that the normalization comes before the attention layers and potentially the feed forward as well, but I'm not entirely sure, so maybe double check. So that's one thing. We then have this swiggloo activation function, which was well, it seems it was introduced by, I'm not sure it was introduced by Palm or they've just taken inspiration from there, but it was introduced in 2020, and basically, again, I kind of looked at this on a high level. Basically, a different activation function that treats things well. Actually, to be honest, I won't say anything that's wrong here because check this out. I didn't have time to go into detail, but it's again an activation function that's commonly used in transformers, basically. And then the other one was rotary embedding. So normally, from my memory at least, we have these sinusoidal embeddings where basically you have different sine activations with different amplitudes and so on. So you end up with high frequency and low frequency embeddings that you then like concatenate together or add together. And this does things a bit differently. Again, a paper a couple of years ago. I actually do think that these two, swiggloo and the rotary embeddings, would be worth doing in their own reading group because they both seem quite interesting. Swiggloo was only about 3 pages long, so I'm sure that one can be done very quickly. But anyway, but there's these two different architectural changes that are slightly different from the original one, which they've taken forward as well, and it'll be worth exploring those a bit more maybe in future reading groups. So then in architecture with Llama, you'll see that the main things they do differently are actually related to the data. There is this one thing they do which helps the scaling to very large networks, which is this grouped query attention. But the main things they do is they have more robust data cleaning. They don't go into too much details about that. In fact, they don't allude to the data set too much, and the data itself is not entirely, not transparently articulated. But they have more robust data cleaning. They updated their data mixers. So one thing they say is that they upweight the factually true content. So maybe they kind of, they don't say exactly the numbers, but maybe they triple the prevalence of Wikipedia data, and they, dampen the prevalence of Reddit data or something. I don't know. So they kind of amplify true sources, and that helps a lot. They trained on 40% more, and this time they double the context length. And then the only architectural change is this grouped query attention, which improves the inference scalability for their larger models. So they say that table 1 compares attributes of the new Llama models with the old one. Well, we'll go to that in a moment, but pretty basic. But let's just quickly unpack the GQA. Pretty simple, actually. So when we look at the original transformer architecture, this famous picture that all of us know, this is what a transformer architecture looks like. Basically, this GQA plays a role in the multi-head attention itself. So let's unpack these. The multi-head attention is then shown on the right, where you have several scaled dot product attentions kind of concatenate. Well, yeah, in parallel, but then get concatenated and run through the linear layer. What you'll notice in the traditional multi-head attention is that all of these heads are independent. They have their own values, their own keys, and their own queries, all duplicated basically. So you can almost imagine it as like, metaphorically speaking, there are lots of dictionaries, these learned dictionaries, these soft dictionaries with keys and values, and also lots of queries that go into the independent dictionaries effectively. What they do with grouped query attention is, instead of having multi-head shown on the left, where the queries, the keys, and the values are all completely disconnected, what actually has happened, I think predating grouped query attention, is there was multi-query attention, whereby basically the analogy is you no longer have a load of soft dictionaries with a load of independent queries into those dictionaries. You now have one dictionary, one soft dictionary, and a ton of queries into it. So you kind of reduce the number of keys and values, and then all these queries come in and query this in this singular dictionary. Basically, I'm pushing this metaphor a bit. In grouped query, you basically do something in between, where you have several queries per dictionary, but you still have several dictionaries, I guess. So just kind of how the alignment between the queries goes to the keys and values. You have more queries, less keys and values. Anyway, they said this makes it scale better. I can only presume when you have these huge models, obviously having fewer parameters, and you want to be able to save parameters in some places. And if this is a particularly efficient way of saving parameters, maybe for a finite amount of memory and compute, it's better to have more layers than to have less layers with all these dense values and keys. It seems though maybe it's a good place to save on resources and use them elsewhere in the model to do more important work, is kind of my takeaway on this. Yeah, so that's the architectural difference. So in terms of the method, so I think maybe, given that we'll do another session on this, like we can maybe focus today on just getting a high-level intuitive understanding of the whole process in general. This is actually my first time fully diving into production grade LLMs, which obviously have this reinforcement learning with fine tuning and all these kind of components to make it chatbotable. So really a deep dive into this for me for the first time, and just getting an understanding of what the whole thing looks like has been quite helpful. So the first step is the pre-training. This is actually very, very simple, as it is with all of the large language models. Basically, you have autoregressive training on this huge corpus of data, where you predict the next character in this manner, where you're just trying to, do pattern recognition in the text, in this huge body of text, pretty much. And that's what they do here as well. So the pre-training phase is the first thing, and they provide a load of benchmarks on that, which we'll go through next. We then have the fine-tuning, and that starts off with supervised fine-tuning, where they have this data set of 100,000 and annotated prompts and desirable responses. So it's supervised training on 100,000 kind of ideal examples of what this chat experience should look like, and you just fine-tune it on that, starting with the autoregressive pre-trained model. And then what you do, so that's a good starting point. It's now looking a bit like a chatbot, and this is when the first version of Llama 2 chat emerges, basically something that resembles a chat interface for the first time from this pre-trained Llama 2. Then when you have this Llama 2 chat, what you then do And again, for people that know how this all works, like, this is, I think, pretty much the standard approach for training LLMs for these kind of applications. But what you then do is basically you want to learn a reward model of human behavior. You kind of want to know what is good and bad behavior for people. So you then collect a large data set. And again, I'm just trying to give a high level to start with before then unpacking all of this in detail, one step at a time. But basically what you want to do is collect a large data set where you have, and what they do is they prompt, the annotators themselves write their own prompts, which they're guided on how to write prompts, but the annotators are independently writing their prompts. They're then getting responses from different checkpoints of the model, different temperature parameters of the model, so that they maximize stochasticity, so they get lots of varying responses. And then the annotator says, well, there's two. There's annotators for safety and annotators for helpfulness, and they basically grade, well, they do a binary classification for which of the two is the most safe or helpful. And then they also give a confidence, basically, kind of if it's very obvious, if it's kind of a borderline decision, and so on. And then basically the idea is to use all of that data to learn a reward model, a neural network that can take prompts and say on a linear level, how helpful is this? How safe is this? And then once you've learned that reward model, you can then do reinforcement learning, because you then have this kind of learned reward model to actually kind of improve the Llama 2 chat model based on this learned reward model, and just do canonical PPO, proximal poly optimization, on the model itself using the reward. The thing is, you do have distribution shifts. So one thing you need to do is make sure these two things happen in parallel. So as the model is being trained using RL, you need to make sure that you continually sample the new model and get new human annotation data to make sure that the distributions aren't misaligned. And this means it's quite a slow process, because annotating this data is time intensive. So you need to kind of update the model and then get a whole new load of annotation, and this iterates for a long time. And this is basically, like, again, slightly like 50,000 foot view of how the whole thing works. Basically, you have, auto-aggressive fine-tuning, auto-aggressive pre-training on a large corpus of open data. You have some like relatively small data set, 100,000, fine-tuning to make it look like a chat interface based on pre-written, hand-annotated, chat dialogue. And then you have this much bigger data. Instead of 100,000, it's 1 million. Binary data set of like which is better with confidence, which then trains a reward model, which then is used in RL to train your Llama 2 chat. And then you have all these other things actually then go one level above to kind of add, like, red teaming and things like this. But we will get into all of the really kind of, the safety stuff in the next session. But just to kind of start off, this is the high level overview of what happens. Any questions on this so far? I know we've not got right into the meat yet, but any questions just kind of like conceptually on how this works?
There's a few questions on YouTube though.
Yeah, I was going to say.
Okay, well, I don't. Well, could you read them out, maybe, James?
Yeah, no problem. So pretty much people were just wondering if they shared the data set that Llama V2 was trained on.
I don't think so. I'm just pulling the paper up now. I'm pretty sure they haven't. So they did. Well, I can get into this a bit. It's actually some of the next slides, because they explain what Llama 1 was trained on, but I don't think it is open source. I won't kind of say that with 100% confidence, but I actually watched another video on Llama 2 on YouTube, and I think they said that it's also not open. Yeah, so I don't think so. But maybe double check on that. Yeah, I think it's trained on open data. I don't think they kind of open source I don't think they open source what open source data. I don't think they say what mixtures and stuff like this, but I might be wrong. Maybe someone could check that behind the scenes by going through the paper quickly or something. Yeah, any other questions, James? Or Vatsali, you got a question?
Yep. I don't know if they
Vatsali?
Yep. A quick question. Just, I don't know if they did, but did they kind of reveal what type of PPO they're using? Because I know there's two. There's one like with like a penalty function, and then there's like PPO2, which kind of checks the distribution. I don't know if they kind of revealed which RL strategy they're using specifically.
I think it's just like vanilla PPO. In fact,
Right.
In terms of the boundary of where we cover this, I just drew the boundary before the deep dive into PPO, so I'll go into that more next week.
Yeah.
But PPO, I think it's just a vanilla one, the original.
Right.
Basically. Yeah.
Yeah, makes sense. Thank you.
Yeah. Was there anything else on YouTube at all, James, or not? Yeah, James.
Yeah. So AN asked, what about overfitting when the model is constantly getting feedback by human grader? I can't really see it. Hold on, sorry.
Although it's not. I think I assume they have a validation set to make sure it doesn't overfit. I'm not sure exactly. Obviously, what you could do is just make sure that you've not overfitted to these like few personal preferences. But yeah, they definitely need to make sure that they monitor that so that it doesn't overfit. I assume with the validation sets they can monitor that and make sure that they don't basically. Yeah, but again, next week actually we can get into those particular things on the RL side in more detail. When I've kind of properly got my head around it in detail. Yeah, I thought this one, because it's quite a big paper, might be worth doing over two. Cool. Any other questions on the YouTube? I guess not right now.
No, not everything. That's everything from me.
Okay, cool. Okay, so so let's first dive into the pre-training, and then we'll go into supervised fine-tuning, and then we can start to look a bit about the reward modeling itself as well. So pre-training. So again, let's first look at Llama 1, because again, this is an extension, so it's useful to have the prior context. So Llama 1 trained on a mixture of several sources, which are all reported in Table 1, that cover a diverse set of domains. For the most part, they use data sources that have been leveraged to train other LLMs, with the restriction of only using data that is publicly available and compatible with open source, which then leads to the following mixture of data and percentage they're representing the training set. So we have, and actually, I can quickly, I don't know if I can quickly share my screen on the paper itself, but basically what these are, so common crawl, I'll have to get Llama 1 open. Give me 1 second, because I can kind of explain what each of these percentages are, could be quite useful. So let me quickly actually share, I'll quickly share my tab of this. So, so it's this one. So yeah, so they have this common crawl, which is what is it? So performs language identification with fast text linear classifiers to remove non-English pages. So I think this is based on books. Pages uses in Wikipedia. Okay, yeah. So there's this and the CI, which is actually I've probably gone through some more detail before, but there's then this thing, and then there's GitHub. So yeah, obviously a lot of code here as well. Wikipedia, obviously, books. They say archive in general, so academic papers, Stack Exchange, etc. Yeah, I don't know if anyone knows what common crawl is actually, because I've not familiar with that. Is it just kind of the whole website, the whole internet kind of, or is it specific on books? It kind of assumes prior context here that I don't have. Sorry?
It's a web archive, actually.
It's a web archive, okay. So just a ton of stuff on the web, okay, makes sense.
Yep.
Okay, got it. And then we observed that using common crawl data set improved performance. Okay, sure. So another common crawl kind of style data set here as well. Okay, anyway, so that's kind of very quick view of that. So basically, they have a lot of kind of web specific kind of web crawl stuff, basically. Yeah. So there's that, and then what they do basically differently in Llama 2, they just mention this point. So they don't mention much in the paper, where they say, oh yeah, Arsh?
Yeah, just to add more to that information, it actually contains 12 years of web data, and that's raw websites, web pages, and everything inside of it. So that's why I assume there's a huge share of common crawl in the data set.
Yeah, makes sense. I mean, I guess that's why this percentage sampling proportion, I guess that's why, I don't know if this is based on how they then feed it into the data or the actual prevalence, but basically data mixtures for pre-training, so sampling proportion. So they basically control the sampling proportion, and I guess they've played with these numbers to get it to kind of, I guess maybe common crawl actually makes them more than 67% in absolute tokens probably, and they therefore sample it down a bit maybe, so you get a bit of GitHub in and Wikipedia, which is maybe a bit more factual than, you know, the whole internet, etc. Yeah. So then what we're doing in Llama 2, they basically say that they get a new mix of data from publicly available sources, which does not include data from Meta's products or services, they emphasize. We made a lot of effort to remove data from certain sites known to contain high volume of personal information. They trained on 2 trillion tokens of data, as this provides a good performance cost trade-off, upsampling the most factual sources in an effort to increase knowledge and dampen hallucinations. So this is the whole data section pretty much. So unlike Llama 1, where they kind of go into quite a lot of detail to explain the data mixes and distributions, this is the entire section in the paper that explains the data pretty much. So I guess maybe the data is open and is good data, obviously, but it's like they don't want, they kind of want to keep a bit of secret source or something, I suppose, perhaps. I'm not sure. Maybe I'm wrong there. Maybe maybe in the actual code it's all there as well, and they're just being brief. I guess maybe someone can message in the comments about that on YouTube. Don't want to paint an incorrect stroke there. Okay, so and then they compare Llama 1 and Llama 2 training data. So again, pretty high level. They talk about the parameters of the different models they train. The context length is now doubled in the new one. YouTube's been a bit unreliable recently. I find it kind of crazy you can't even edit the videos as well, but okay. Okay, let me, well, maybe just get someone to confirm it's working now. Okay, great. Okay, well, anyone that's watching live, sorry about that. We're having a few issues with YouTube for some reason, stopping the stream midway through, but hopefully it's working now. Obviously, James, if it cuts out again, let me know, and we can get it fixed. Yeah, cool, thanks. Cool. Anyway, so yeah, so back to this. So it seems though, well, not only it seems, it is clearly the case that there is still more learning to be done on the data. Now, I don't know, I mean, I had a look at the paper. They didn't really seem to articulate whether that means that the model can keep doing better if they train it for longer, or whether it's just going to start overfitting. I'm not entirely sure, but it certainly hasn't saturated. They didn't mention or articulate that this means that there's a new Llama 3 coming out that's going to be another trillion, another trillion pre-training tokens that's going to improve performance further. I'm not sure. I mean, I was reading through it quickly now, but they don't really elaborate on that. So apart from them to say that it hasn't saturated yet. So yeah, let's see what that means exactly, and maybe you can get better performance by just continuing this pre-training phase. So yeah, then they talk about CO2 emissions, and basically the total training, when you look at all the models and the GPU hours and the power consumption, it ends up being trained for 380 years pretty much, when you kind of look at the GPU hours that are used. And then this is 540 tons of CO2, if I'm reading that correctly. So yeah, quite a lot to train, but their point being, and that's just, to be honest, for me, not so much an indication of how much this model takes, but obviously just an interesting data point on just how much what this means to the environment when you train these huge models. But it's definitely interesting data, and it's nice that they put it in the paper as a means of transparency. They make the point that, of course, like, this is gonna, the fact that it's open source means less people will need to train their own models, and therefore it's a very good thing that it's open source and that it's offset by Meta's sustainability program, etc. Yeah. Anyway, so quite a lot of CO2 that these big models are generating. Anyway, is the main takeaway here. So pre-trained model evaluation. So this is all just the pre-trained stuff. They test it on this code. So on this human eval benchmark, on this common sense reasoning, on this world knowledge, so kind of like factual questions, this reading comprehension, maths, and then this popular set of aggregated benchmarks. And this is just, again, no chat-based interface, no reinforcement learning, just the autoregressive trained model and how well this does. And I have some results here. So overall performance on grouped academic benchmarks compared to other open source base models. So the base models of these big LLMs. And what do they get? So that they put Llama 2 at the bottom, and basically their stuff is by and large better. So I mean, let's look at this. Like, we have the size, we have the code. So on code, this is the best compared to others. Yeah, common sense reasoning, it's better as well, although it's quite close to some others like Falcon 40 billion is pretty close to the Llama 70 billion, for example. Again, Falcon not a million miles away on some of the Llama variants. The 50, for example, yeah, I mean, maybe if Falcon was bigger, it would get similar to the Llama 70 billion. But yeah, anyway, but it's competitive and broadly speaking, better than the other stuff out there. But it is also bigger, of course, than either the MPT or the Falcon model that they're comparing to here. It'd be interesting to kind of just see what it would be like if it was Llama's smaller model. Because again, like, I mean, the MPT 30 billion does better on code than the Llama 2 34 billion, for example. So I think a big point here is that this is a bigger model and the size, you know, means something. It doesn't necessarily mean that the training pipeline, the architecture, or anything else is superior, but the size obviously brings something with it. Yeah, it's my main takeaway at least. And then in some comparison to closed source models, again, this is just the base autoaggressive train model. So results for some GPT 3.5 and GPT-4, and also for Palm model. And these benchmarks are again the same kind of benchmarks again. GPT-4, they do compare to GPT-4 Hoya, which is actually, you know, a lot better on a lot of these, to be honest. When you look at the numbers of GPT-4 and Llama 2 on all of these, they're big differences. So GPT-4 is still, you know, by and large ahead of the curve here, but it's not too far off. I mean, it's not too far off GPT-3 on the MMLU and the GSM8K. Oh yeah, but it is quite far off on the human eval. Yeah, so still a bit of catching up for the open source LLMs, but you know, a good start. Okay, so that's the pre-training phase. So now we're getting to the fine-tuning phase. So again, the first phase of this is the supervised fine-tuning. So we start here. And basically there are, I think it's 100,000 examples, that's what they said at the beginning, of handwritten prompts and responses like this. So for example, so they give an example of helpfulness at the top where, let's say, write a poem to help me remember the first elements of the periodic table, given each element its own line. So this response was written by an annotator, so quite a poet, it seems, in the annotator team. And the bottom one was a safety annotation where, although I find this a bit weird because I guess as part of the template, as part of the annotation guidelines, basically they just have a copy paste response. If it's not safe, obviously it would seem a bit strange for people to be asked to write their own "I'm sorry, I can't provide an answer" like response. So I actually think they probably have a copy and pasted one, but I'm not sure about that exactly actually. But in any case, they do this kind of supervised training where it's as simple as here's the prompt, here's the response, and then what they do is they zero out the loss function on the prompt and only have the loss it back propagated through the response. Basically, they then have this like special token which separates out the prompt and the response. Again, I think quite standard for this kind of stuff. To basically take this base model and train it to become a chat-based agent, basically, where obviously the loss only goes through the response. That's what the model's doing, and also it has this token to kind of make these clear breaks between the different phases of the back and forth chat, basically. Yeah. So with that fine-tuning, again, I mean, all the training data, the loss rate, all this kind of stuff is there in the paper. I've not bothered unpacking all the kind of low-level details without having kind of, you know, deep insights into what they mean. With all these papers, there's like random learning rates and stuff. It's just whatever worked best for them, obviously. So that's the supervised fine-tuning phase. We then get into the reinforcement learning with human feedback phase. So the first thing they do is that they collect this data set of human preference. And I believe that they collect, oh, here we go. So 1.4 million is the size of the data set. So a very large data set where basically, and I'll have to just kind of explain this in words a bit. And in fact, I think at this point in the talk for the last 10 minutes, I'm going to quickly open up the paper because actually that's probably going to be a better way of presenting this because I've not really got the best slides for this. Oh, sorry, let me quickly share this tab. So we now get to fine tuning. There's the supervised tuning. Again, they make these points. Let's like quickly look at this as well. So I talked about the supervised fine tuning. This is some examples. They also, a few things to Bootstrap, they get started with the supervised fine tuning stage with a publicly available instruction tuning data. So they actually also use some public annotation data for this. They make this point of quality is all you need. So the third-party supervised fine tuning data, available from many sources, but they generally found that it has insufficient diversity and quality, in particular for aligning LLMs towards dialogue style instructions. So they focused on collecting their own several thousand examples. I think it's about 100,000, as illustrated in table 5. So this is kind of the examples we saw earlier. And again, by setting aside millions of examples from third-party datasets and using fewer but higher quality examples from their own vendor-based annotation efforts, the results notably improved. So again, this kind of recurring theme, which people have known for a long time, which is it's not the quantity of data, it's the quality. And also similar to in spirit to the results of this paper, where they also find that a limited set of clean instruction tuning is much better than a ton of data. And they, in the order of tens of thousands was enough. They stopped annotating supervised fine tuning after collecting a total of 27,000 annotations. So I guess because at the beginning they mentioned 100,000, or at least on the page, on the landing page of the thing, they mentioned somewhere, supervised fine tuning over 100,000. That's like on the landing page of Llama. So I assume that's like 27,000 of their own structured fine tuning mixed with kind of 75,000 of the open stuff, I suppose. But yeah, anyway, so that's that. And then the fine tuning details of just the learning rate and everything. So then we get into the RL with human feedback, and then they outlining in length how they do this human preference data collection. And again, it's so you can align the model with human preferences. This is of course very important. And again, the annotators select which of two model outputs they prefer. This is then subsequently used to train the reward model, which learns the patterns and the preferences. And then the reward model is also used to train the RL algorithm that trains the actual final model. So I'm just going to kind of quickly blast through the key points here. So again, such a long paper and so little maths that just lots and lots of text. So they choose a binary comparison protocol over other schemes because it just enables people to just do very quick feedback. Obviously, it's very good to get results quickly. And then they leave other methods for future work. So that basically they ask annotators to first write a prompt. They then choose between two sampled model responses based on certain criteria. In order to maximize their diversity, the two responses, as I said earlier, are from two model variants with different temperatures and high parameters and checkpoints, etc. So that you get a lot of diversity. So they have to choose which is the best, but they can also basically assign a confidence. So they say whether it's significantly better, better, slightly better, or negligibly better, or unsure. So you can kind of say how strong a company you are. So for their collection of preference annotations, they focus on helpfulness and safety. They do these separately. So they have different people. I mean, I won't read the whole thing out, but they basically have some people doing it for safety only, some people doing it for helpfulness only, and their argument being that they found easier to kind of give very clear guidance, particularly seeing as the annotators are generating the prompts themselves as well. They don't have the annotators needing to do too many things. So some are doing feedback on safety, some on helpfulness, and then these reward models are also trained independently. So what they then do is they take the base model, which is the pre-trained model, and they use that as a starting point. They change the head to just have a simple regression loss to the score, and then they train this reward model, train this this helpfulness model, and they also articulate that the reason they do this, the reason they use the pre-trained base as the starting point, is because they want the reward models to know what the actual model itself knows, and therefore their argument being that minimizes the chance of hallucinations, because you kind of know when the model does or doesn't know something to some extent. I kind of understand that on a high level. I kind of thought about the intuition of that, but I mean, kind of knowing is also a slightly humanizing word or something. But basically, you want to make sure that the reward model kind of has access to the same weights that the other one does, so it can kind of maybe see when it's using things that it's learned in the trained data and when it's trying to make things up and so on. And it kind of has access to that shared, that shared structure, so it can kind of understand when maybe the model itself is making things up, basically. So this is that. Again, so then they just compare their data set. Anyway, this is the table we had in the deck. We then have just all these other data sets that exist. There's Anthropic has created some, OpenAI has created some, where there are various different token length, for example, and turns per dialogue, etc., of this kind of helpfulness and safety data, which is all about capturing human preferences of LLMs. This is what all these data sets do, and they're comparing their data set to others in the field. So then what they do is they then, sorry, where are we? Here we go. So they then train this reward model, and they convert their collected pairwise human preference data into a binary ranking label format, chosen and rejected, where they enforce that the chosen responses have a higher score than the counterpart. So it's a simple binary ranking loss. So basically, you have this reward model which takes in the prompt X and the completion, the response Y, based on the model weights theta. And then YC is the preferred response the annotators have chosen, and YR is the rejected response. And then basically this loss wants the score of the chosen response to be higher than the score of the rejected response. And this is how you then train the reward model. And obviously the parameters theta are being updated. Again, the theta start as the pre-trained ones, then they're updated according to this loss. And then what they also do, because you have this extra confidence information, which is useful and actually provides additional details about, let's say that you said that this response is helpful and this one is not helpful, and you're very, very confident about that. Then, of course, you can actually increase this rank loss further and push them further away. So you then have this margin parameter, which is basically a discrete function of the preference rating. So I guess, like, if it's high, then it's like a step function, and then if it's something else, it's another value, and it's just like a step function based on these 5 preferences, I guess. Yeah, and they use a large model for pairs with the distinct responses, of course. So that's how they train it. So that's the reward model. They talk about their data composition. Also, while I'm here, any kind of questions on this so far? Any kind of thoughts or questions for the time being? No, okay, I'll keep going. So the data composition, they combine the newly collected data with existing open source preference data sets. So they mix it with some of other open stuff. I think they tried various different mixtures. So how in Oxford do you not observe negative transfer from the open source data sets? So they make this point that they use open source data sets because it improves generalization, which would make sense, because obviously if a reward model is only trained on this data that's all come from Llama 2, then there's a chance that Llama 2 could learn to cheat this reward model. The reward model is only generated from data that has come from prompting Llama 2, whereas they say that, well, actually, if we then use helpfulness and safety open source data sets which have actually come from other models, it maybe just kind of makes the reward models more robust, less susceptible to kind of being hacked by Llama 2, trying to minimize the loss function of the reward and so on. So just training on these open data sets doesn't seem to degrade performance, and therefore they do that as well, and they mix it in. Do not observe negative transfer from open source data sets. They've kept them in the mixture model, and they could make better generalization, as I said. So then with training data available from different sources, they experimented with mixing recipes. I think at the end, they just did like half experimentation. It's trained on all, combined with an equal part of the remaining data univocally sampled, so a pretty basic mix. They then do some of the mix in terms of, these are all kind of implementation details, obviously. And then in terms of the helpfulness, they mix, I think, meta helpfulness and open source helpfulness in 90-10. So they really strongly weight the helpfulness from meta, and they have a tiny amount of open source helpfulness data. They found that setting this 10% is beneficial. Anyway, so that's what they do there. They trained for 1 epoch on the training data. They found that training longer can lead to overfitting. And then in terms of these tables, and then we're getting towards the point at which I was going to cut off, which is when we get into iterative fine-tuning, where we can go into a bit more detail next time. But basically, they So yeah, they talk about the training details. With this one, they talk about the performance of their final helpfulness and safety reward model. So these are accuracy values from 0 to 100%. On a diverse set of preference benchmarks. So these are the models on the left. So this is their reward models here, and these are the data sets, and these are the accuracy in terms of predicting a held out validation set where like we assume that the human annotators are, let's say, correct in their decision, whether it's this one or this one, which is more helpful, and then it's how many times that the model agrees, and basically, and they have their own held out data sets, they have the other helpfulness data sets. They note that the meta helpfulness model does better on the helpful data, and the safety model does better on the safety data. Obviously, like in terms of these evaluations, this is the data that was generated. So the data generated in helpful and meta safety is people prompting the models in thinking about helpful content and safety aware content, and this is kind of the data distributions are therefore a bit different in terms of the prompts that are given for the helpful and safety. Of course, on these validation sets, they then do create like scores that for example, take the helpful data and assign safety scores to them as a kind of a ground truth accuracy to try to attain. But they say that the data distributions mean that the helpfulness or the helpfulness reward model is better on the helpful data than it is on the safety data, and likewise the safety model is better on the safety data than it is on the helpful data. So they've kind of overfitted to the data. They've overfitted to the data distributions a little bit, because ideally the safety reward model should always be as good as the people are at predicting safety, but it's not. It's much better at doing it in the safety generated data. So there's a bit of non-generalization appearing there. And yeah, then they compare to other benchmarks where their reward model is better than the reward models by and large of the other reward models, of some of the reward models that are out there, basically. And then they basically make this observation here as well, which is to say that they are better on the high confidence example. So basically on all the examples where the annotator, which is, I mean, kind of, I don't know if it's worth presenting this, it's kind of obvious, but the annotations where the annotator was very confident about their decision, basically their reward model does better on those than it does on the ones where the annotator was unsure, where actually in some cases it's only marginally better than chance. It's only marginally better than 50%. In the cases where the annotator really, and probably the responses were very close, and actually this is very much a subjective decision, and of course the model can't really, at some limit, can't really be predicted to predict the human preference that this is all being graded against when you have the ground truth. So yeah, anyway, so that's some points on the reward model itself. Again, they really go into a lot of detail here, and then I guess in the interest of time, the last thing they present here is basically the scaling trends, so that they make this point that they study the scaling trends in terms of data and model size for the reward model, fine-tuning different model sizes on an increasing amount of reward model data, which is collected each week. And figure 6 shows the trend showing the expected result that larger models obtain higher performance on a similar volume of data. So basically, red is higher up than green and blue on the same amount of data they've collected. So, more models with higher capacity are able to model the rewarding better and quicker on the same data. This is expected. And then more importantly, the scaling performance has not yet plateaued. So again, they kind of made this point that even now things keep getting better. So I guess maybe this is all pointing to a future where Llama 3 gets released, because they're still doing all of this ongoing stuff, I imagine, and there's still people continuing to improve the reward model and continue to improve the base model and so on, with the continual training of the current model. It is what I interpret this to say. And signal on there is the room for more improvement with more annotations. We note that the reward model accuracy is one of the most important proxies for the final performance of Llama 2 chat. While the best practice for comprehensively evaluating a generative model is an open research question, the ranking task of the reward has no ambiguity. I mean, because effectively this is modeling exactly what people want and expect from these models. So that's the point there, and therefore everything else being equal, if you can improve the reward model and get that to much more accurately reflect human preferences in terms of safety and informative, goodness, yeah, how good the information is, then this will directly translate into improvements for Llama 2 chat. So they've made this point that even now, like, it hasn't plateaued, and the reward function continues to get better with each successive batch stage, basically. But also, because this then feeds into the next section, what I would say is that the reason there are these batch stages is because what they actually do, these things interplay. It's not like you just take the base model, which has been pre-trained only, and then you just do a ton of reward like annotating. What you actually need to do is continue to train the model with reinforcement learning so that the distribution of the model moves to a new place, and then you need to see, then you need to generate new annotations which are on distribution of the current model and what it's doing to then improve it. Because obviously, if you're using old data of an old model, it's not that information, not that useful anymore to move the model, because it's already kind of, let's say maybe overfitted to this data, and it doesn't know where to move next. And you need to then provide more guided data on the current version of the model, so it knows how to improve its current self. And therefore, this is why it's this slow iterative cycle of training the model with RL, generating a ton of new data, and then having these batch stages along the way. And I assume this is ongoing as we speak, to just keep crunching the numbers and getting them better and better and better. Okay, well, anyway, in the interest of, so what we can pick up with next week, again, I decided to not give a 50,000-foot view entirely. I wanted to go through each of these sections in a bit more detail, but certainly in one more hour next week, we can go through the iterative fine-tuning. We can go through the reinforcement learning algorithm and actually a lot of the safety stuff. You might be a bit dissuaded by the where the cursor is right now, but there's a huge amount of appendices and references that we won't unpack all of. We'll just go through the body of the paper. So in one more hour, we'll be able to go through everything. And I think it's worth it for a paper like this because it's made a big splash in this very big and important LLM chatbot space. So understanding it in detail is not a bad idea, I think. Okay. Well, any questions on that so far? We're obviously cutting out before the end, but any questions from anybody? Yeah, James. Should I keep the paper open? Why not?
One from YouTube from AN asks, because all their models in Llama 2 were trained on 2 trillion tokens, so their smaller models outperform other open source models.
Their smaller models didn't really massively outperform other models. I didn't think they did on some stuff, but when we look at their base stuff, although they do here look obviously on their own curated thing. Maybe that's because of the latest stuff. Because so if it's about the 2 trillion, then what we should be looking at is the base model performance, because this is where there's nothing else, none of the reinforcement learning and all those bells and whistles. So if it was because of the 2 trillion, then we would expect to see these results being better, because this is testing the base model with nothing else done. And yeah, I don't think it is massively better. Like this is 27 Falcon. Well, it's better than this actually on code. That's true. But it's not better than MPT on code. What about this? Like Falcon is 69, Llama 2 69, so very similar, slightly smaller, but again, obviously looking at the bigger ones, it's better. But Falcon is 56 on this. This is 58, so a bit better, a bit smaller. Yeah, maybe it's because they've trained it from. I don't know how many tokens the others were trained on. It might be that they've just trained on more tokens, but they've also. It's hard to say. They've also done this. Like I forgot what it's called now, GQB or GBQ or something. This kind of sharing of the queries with a smaller number of keys and values is one thing they've done. Maybe that makes a difference. It's hard to say exactly why, but it's not jaw-dropping, obviously. Like they mention these big improvements on the final thing at the end on these human evaluation metrics, but I think these things have much more to do with the intense amount of effort that's gone into the alignment problem after the pre-training phase, basically. Yeah. Any other questions at all?
There was a question by Peter on the Google Meet chat.
Okay. So let's have a look. So earlier they claimed they did reinforcement learning with human feedback on page 14. They then say until RLHF V4 we used only rejection sampling fine-tuning, and after that we combined the two sequentially, applying PPO on top of the result of rejection sampling checkpoint before sampling again. Does this mean that they really did rejection sampling fine-tuning for the majority of the alignment step? My short answer to that is I don't know. I've not read that part of the paper yet. So maybe save that question for next week when we dive into the RLHF stuff. Basically, I had intended to do the whole thing in one session, but a combination of not quite having time to go through it in as much detail as I would have liked, and also it being like a 70-page paper, I thought we'd kind of save a bit for next week. Basically, also save someone else on the team from needing to present as well. So can delay that a bit and save somebody else a bit of time. Yeah, so maybe hold that thought, and maybe on the beginning of the next video I can come in with a good answer. Any other questions at all? Yeah, well, maybe except for next time. Any questions? Well, Harris is dropping you in a bit about Salia. Do you have any questions about Salia, or have I answered them all perfectly?
Nope. You've answered them all perfectly.
Okay.
Yeah.
So I like to hear. I'll assume that's the reason, not that I've confused everybody. Wishful thinking.
Yep. No, greatly presented.
Cool. Okay. Well, anyway. Well, thank you. Well, we're at time now anyway, so I guess we'll yeah, stop it there. But as I say, we'll continue the conversation this time next week. I'll actually get the whole paper read properly, and we can kind of then have a full holistic view. But hopefully that's given a bit of a 50,000-foot view of what's going on, a high-level overview of all the different components, and a bit of a detailed view then of the pre-training and the supervised fine-tuning and the reward modeling. And then we'll go into how the reward modeling is used during the reinforcement learning phase, how they do safety checks on top and everything, blah, blah, blah. And we can go from there. But yeah, thank you very much for listening, everybody. Thanks a lot for following along on YouTube as well. And I'll see you guys all again at the same time next week. Thanks a lot. Bye, everybody.